Hi, everybody. I'm Dan Abadi, professor at the University of Maryland in College Park, and I'm here to speak today about uh, different ways to handle data federation and data virtualization, what's the right way to build such systems, and how to scale them, and some challenges which come up, which may cause some scalability issues. So quickly about myself, I'm a professor at the University of Maryland. I've been here 7 years. Before here, I was at Yale University for 9 years. And before that, I was a PhD student at MIT. And in my lab, what we do is we do research in database system architecture and implementation. We build scalable data systems, and interested in different ways to bring them to the real world via startups and via working with companies in the build scalable systems. And recently, in my lab, we've gotten interested in data federation and data virtualization, and some of the technical challenges which come up in this space. So many people, they don't know what it's federation has been a niche within the database world for a long time. But many people never heard the term or are not used to the term. So before we jump into how to build the systems, let's quickly overview what is data federation. So, so let's jump in with an example. Let's talk about how data federation works via a retail example. Let's assume we are a retail company and we have data in different database systems. Let's say we have some transaction data. We sell products, and every time we sell a product, we store information about that sale in a database somewhere. In this example, it's in a Teradata data warehouse, but it can be anywhere. It's just some database which stores information about products which are sold. And the information may include things like the customer that bought the product, or the product which was sold, the date or the time that it was sold, the amount it was sold for, the location, other things that may come up, the order that it was part of, order ID, the information that may be part of the transaction. We may also have other data stored in some other database. For example, let's say we decide to launch a loyalty program, and we contract with some external company to get that started for us, and that company uses ScyllaDB or some other database to store loyalty data, the customer information, the names, the addresses, other things we know about our customers, phone numbers, whatever. It may be in some other database stored by some other software product. It's not unusual for large companies to do this. And the problem that comes up in this space is that if you have your data stored in two different software systems, it's very easy to have those systems siloed off from each other. In that you may have some queries which are loyalty queries which go to the loyalty data set. You have some other queries which go to the transaction data set, but it's very hard to if you have a question which spans both data sets, it's a little bit tricky to express queries over both data sets since they are stored by different systems. And just to make this example more involved, let's say that we also have another system. Let's say we have some information about data stored in a social network. And that information is in a data lake that is in the cloud somewhere, Amazon or Microsoft or whatever. It's in the cloud. And maybe that data sets are in open formats, not in actually any particular database vendor. And they're stored in the cloud. And again, it's separate software stored somewhere else. So now we have three different different data sets stored in different software systems. And the question is, how do we express queries if we need to have a question which spans different data sets? So one solution to deal with this is to use what's called a query federation engine or a federation system. And what they do is you send the query, it's like a layer above the systems, and the query comes in, and the federation engine analyzes the query and figures out, well, this part of the query is relevant to the data in the social network data set, and this part is relevant to the loyalty data set, and this part is the transaction data set. And it'll divide the query into subqueries, sending subqueries to each system which contain that part of the original query which is relevant to which accesses data for that part of the data set which is relevant to that query. So you send the subquery to each software system for each data set. Each system runs that subquery, and then sends the result back to the federation engine. And the federation engine then takes the results back, combines it together, and sends the results to the end user. So that's the basic idea. And at the end of the day, what it's doing is creating a interface, is creating sort of like this impression to the end user that even though we have data in different places and different systems managed by different systems, it's as if we have one giant database. We give the image, the impression to the end user that we have just one giant database, and that's very nice. It makes life much easier to work with databases, to work with data sets if there's just one big interface to access everything. It's a really beautiful vision. The problem is there are many technical challenges to make this work. For example, one issue that comes up is that different systems have different interfaces. So, for example, Teradata may have a SQL interface, a standard SQL interface. Scylla may have a different interface, say CQL. Maybe we query our data in the data lake via Spark SQL, something like that. And each interface is a little bit different, although they're all based on SQL. But there are differences in the way you express queries in those different interfaces. And many times, systems will have extra functions beyond the standard SQL or CQL that they generate to encourage the users to get lock-in. If they give you additional functions to access to do extra special analysis procedures, if you use them, now you're kind of stuck using that particular database. So beyond the standard interface, the standard SQL or other interfaces they provide, they often have additional functions which you can use, which are specific to that system. Now the problem is the federation layer has to know how to use how to write optimal queries or accurate queries using all the different interfaces, all the different systems. And that can be a challenge because since they're all different, it requires the federation engine to have a lot of detailed knowledge, a lot of understanding very specifically what's the right way to express what I want in the different languages and using the functions which are available in different systems. And it adds up being also a maintenance cost as well, because as systems change, as they improve the way or add new things to the interface, we have to use those. So we have to maintain that cost over time. That's one issue which comes up. Another issue which comes up is the issue of query optimization. In that the way the query optimization works in a traditional system is that the query comes into the system, and we analyze the query and we figure out what are the different ways I can run this query. And there are many different ways. If you look at different ways, different operators you can use, the different type of operators, the different ordering of operators, and very quickly, for non-trivial queries, you can get to hundreds of thousands, millions, even more than that, of different options which could exist to run any query. And all of them have the same exact result. It's just the way you do it is different. And they could be orders of magnitude in performance difference. One option may be a few seconds, another option could be a few days. It could be a very big difference in the time to run that same query. And so the way that a traditional system figures out what's the right way to do it is they will sort of cost the different plans. They'll say, well, this plan we expect to be very fast, this one's slow, this one may take 2 seconds, this one 5 seconds, this one 20 seconds. They will sort of, in advance, estimate the cost of running each plan, and they'll choose the lowest cost plan. The problem is for the federation engine is that in order to cost out a plan, they have to know how the underlying system will do their part of the subquery, their part of the plan. And since it's a different system, since we are the federation layer, we're sort of administratively separate from the underlying system, we don't know exactly how long it will take to run a particular plan. It's a little bit of a black box to us, and so that's so we may end up choosing the wrong plan, and we end up getting maybe a problem for us. We'll end up choosing something which is way too long. It could take orders of magnitude slower because we chose the wrong plan, and getting it right is very hard in the federation system. That's another issue which comes up. Third issue which comes up is what about resource? What happens if certain systems we're running over are underutilized or overutilized, or they're under-resourced? So, for example, it could be that Teradata right now is being used by a ton of other queries from other systems, and so when we issue a query to it, it's not ready for it. It can't handle it. It's just overutilized right now. So we may choose a different plan if we know Teradata is currently overworked and not really able to handle queries right now, or at least not handle them fast. So that's another issue. Because we're a separate system, we're not really on top of who is currently overworked and who's currently underworked of the underlying systems. That's another issue which comes up. So these issues are actually major issues. What happened was that although the vision has been around since the 1990s or even before that, systems have been around for a very long time, they never really took off. The vision of having one giant interface for all your data, it's a beautiful vision. It's just not practical. It's just too hard to make it work in practice, to make it fast, to make optimized queries, and to speak all the languages of the underlying system. It's just too hard. To do it really well, to do it really the way we've envisioned it. So in practice, what people mostly do now, these days is they take the data in different data sets. Let's go back a little bit. And they take the data where they were, and they move it to one location. They do what they can. They have a giant centralized IT team somewhere, and the IT team is in charge of taking the data sets which exist, wherever they may exist, and try moving them around to one big location and have it all in one place, and then send the queries there rather than doing it in some federation layer. That's basically what has been the preferred approach, rather than using federation the way we envisioned it originally. So it never really died, but never really took off the way we expected it. And then there was a period where it took off a little bit. It got a new name, data virtualization, which is a little bit more of a broader term than data federation. It has some additional features, but at the end of the day, it's basically the same thing. It's basically a layer above all your data sets, which is there to provide a single interface to all your data. So that took off for a while as well. It kind of had like a re-emergence, but at the end of the day, the same problems showed up, the problems of data maintenance, code maintenance, the problems of optimization. They still never really took off for the same problems, and therefore kind of ended off in the same place where federation ended off, of never really taking off. So that was, that kind of where what happened, I think where things were until recently. But now the last few years, since 2022, 23 or so, until now, there's been this surprising reemergence of data federation and data virtualization that kind of took a lot of people by surprise, where almost every major database now has some federation feature. So for example, Databricks, they announced 2023, they have a federation feature. Snowflake and Microsoft announced something in 2022, I think it was. Teradata had Query Grid designed to federate across different external systems. ClickHouse had something, federation option recently. Redshift announced their federation option recently. Dell with Starburst had their virtualization option. Denoda with their virtualization option. Just tons of different major companies that work in the data space all of a sudden announcing federation systems. So why? Like, what's going on here? What's the reason? What's behind this reemergence? So one major reason behind the reemergence is that the architecture of how to build federation systems have changed. It used to be entirely push-based systems, like you saw before in the first few slides in this deck, where the query would come into the federation engine, we'd take the query, we'd push it down to the underlying system, and then the most of the work would be done in the underlying systems, in the Teradatas or the Scillas or the Sparks or whatever. The underlying systems would do most of the work. In the pull-based approach, instead, what we're seeing now is that the new generation of federation engines, they push down almost nothing. Basically what they do is aside from very simple predicates and filters, they extract the raw data into their system. They do the vast majority of the work inside the federation engine, and that has solved two of the major issues we saw before. Specifically, if by pulling the raw data into the pull-based engine, it needs to have a much less of a knowledge of the APIs of the underlying systems. We saw before that each system speaks a different language of different API, and the federation engine had to have a very detailed knowledge of how to speak the different APIs of the different systems. But if all we're doing now is we're just extracting raw data, then the extraction of that data, the knowledge of the API to extract data it's a much narrower API. It's a much simpler API to know how I get data out of your system than it is to express queries of that system. The query languages are much more detailed and specific than just the interfaces used to extract raw data out of the systems. So it's by switching to a pull-based approach, you kind of solve the maintenance problem behind having to know the different languages of different underlying systems. That's one issue. The other issue that they solved with the pull-based approach is that the optimization problem is now much easier, because now, since we're doing the majority of the work in the federation engine, we don't really have to care about how the underlying systems are doing anything, because we're doing everything ourselves now. So the black box problem of not knowing the details of how the underlying systems are running queries goes away. Now we're doing everything ourselves. So the optimization is now just local optimization. That's a much easier problem than remote optimization. So it solved two major issues. The problem is that at least in theory, it doesn't scale as well, right? Because the push-based approach is really just kind of pushing code to data. We take the query, we're taking that query and we're pushing it down to the underlying data sources. So we're taking the query and sending it to the data, the code of the query, and sending it to data. Whereas the pull-based approach, we're taking the data and we're pushing it to the code. We're taking it out of the underlying systems, we're taking it across the network and into the federation engine. And that's pushing data to code. In theory, that should be much worse. From a scalability perspective, code is much smaller than data. Code is maybe a kilobyte, less than that even. Data could be terabytes or petabytes, a huge amount. So in theory, at least, the push-based approach should scale much better. In practice, though, we saw it doesn't. And the reason why is because it's just very hard to optimize queries over the pull-based approach, the push-based approach. So in practice, and what we see now is that by switching to the pull-based approach, it solves, by solving the query optimization problem, making it easier at least the query optimization problem, it actually makes things scale better and not worse. And part of the reason behind that is that the real problem with scalability by pushing data to code is the network. Is that if the network is a bottleneck, then the pushing data to code is a very bad idea. But today it's just not. It's just the network is often not the bottleneck. Often today, really, the network is much less likely to be the bottleneck than the processing of the systems. And so therefore, it's often very possible, and we see it today very often, of shipping terabytes or more than that over the network on the fly at query time, and it all works out to be just okay. So that's one sort of point, or one major reason why the pull-based approach has been very successful. There are other issues which come up. I'll say briefly, we don't have time to go into a lot of detail, but JDBC can be an issue because in the pull-based approach, you may get stuck behind extracting data over JDBC over some kind of connectivity interface, which streams the data tuple by tuple, one row at a time, which can slow things down. But modern systems to get around that via having multiple different threads, they send like 5 or 10 different threads of different connections to the underlying system to get data faster in parallel across the underlying systems. We can't go into too much detail, but there are ways around it that sort of solve that particular scalability problem. Other drivers behind the pull-based approach is that more and more data is stored in open data formats now. It ends up being much cheaper. It goes from say 10 or 20 cents a year to store data in open data formats on something like S3 and object stores like S3 in the cloud than it is to store data in commercial database systems. Which can be tens or more than that of dollars per year per gigabyte. It's just much cheaper, orders of magnitude cheaper to store data in open data formats. So we're seeing more data stored in open formats, and as a result, vendors had to deal with it. They had to say, okay, you can store data in my system as well, but I had to provide an interface for you to be able to get at the data which is stored externally. So that's been another very important driver behind the takeoff of adding federation features in modern scalable data systems. So moving forward, there's still a lot of research problems in the data federation and virtualization space. So one issue is that we described before, that now the big trend is moving everything out of the underlying system to moving into the federation engine. We've gone too far in that direction. Now, almost everything, we're sending too much raw data over the network. Everything is moved, and we don't have to go that far. There is a nice sort of midpoint between a pure push-based approach, where we push everything down, and a pure pull-based approach, where we pull everything up. There's a nice kind of in-between point, and there's a bunch of research going on right now in my lab and other labs to figure out what is the right midpoint between those two different approaches. That's one area. Other issues that come up are supporting writes. So writes through federation engines are still a big challenge today. That's something that's active area of research, and also data integration. So it's nice if you have a nice interface for everything, but still, if your data sets refer to different IDs and they don't really sort of work together nicely, that they kind of refer to the same thing in different ways, integration is a little bit of a challenge to express queries. Even if you could access the data, if you can't express correct queries, that's still an issue. So there's still a lot of research going on in my lab and other labs. And so a lot of these questions, we've published some of it is active. And that which we published already, some of it is summarized in a book we wrote recently in O'Reilly. It's available now. If you have a subscription, you can download it from O'Reilly. If not, you can email me. I can send you a link to the PDF version of the book. It sort of describes a lot of what we talked about today in more detail, the approaches which are taken in the past and currently and in the future, and how we should do things with a hybrid approach is all discussed in the book. So please feel free to email me or contact me in any other way, and I'm happy to speak to continue conversation offline.